Okay, welcome to the class, and what we are going to discuss today is PUCCH transceiver chain. Okay, so we have been looking at PDSCH, PDCCH chains. We have discussed them in great detail, and this is what is remaining, PUCCH. Okay, we will discuss that, and now we are going to discuss basically two different formats of PUCCH which are defined in the standard. We will focus only on these two. Okay, once we understand these two, rest of the formats can be easily understood. Okay, so what is basically this format 0? Format 0 is a short duration PUCCH chain, okay, which essentially means that it is meant for sending short information. Okay, and look at this format sends maximum of 2 bits. Okay, so but you need to design a transceiver chain for that also. Okay, right, and it spans 1 or 2 OFDM symbols, and typically it is used for sending hybrid ARQ, ACK or NAC. Okay, right, it is 1 bit, we know that. Okay, so but it can send maximum of 2 bits. Okay, 2 bit of information, and you see how crucial this is. Okay, if ACK and NAC, if ACK becomes NAC, then you will basically retransmit the data even though user doesn't require it, right? Okay, and NAC becomes an ACK, that's a bigger problem because user will keep waiting for the data and never come. Okay, so user will time out. Okay, so you see the importance of it. Okay, and there is another format. This is also short duration. It transmits more than 2 bits. That also spans 1 or 2 symbols, and it is used for sending CSI reports. What do we mean by that? It's basically who's going to send the MCS information. Okay, if it is user is only going to send the MCS information and it's going to send using PUCCH. Okay, so you see that all the dots are getting connected. Okay, so even before the downlink transmission happens, user has to send this, right? Okay, and so it will this will discuss about it because we have not spoken about it, but you should know that like this, it is used for MIMO to enable MIMO transmission also. So we will see this format 0 chain first, and then we will look at format 2. Okay, so format 0 transceiver chain, the first bullet what it is saying here is, let's say there is this ACK or NAC, 1 bit ACK or NAC. What it does is it takes this 1 bit ACK or NAC and then it uses a 12 bit random sequence to map it, okay, to 1 bit to 12 bits. Okay, and that's how it is generated. Okay, that this 12 bit sequence, what is this? This is the sequence. Okay, and what are we doing here? You are taking this sequence, correct, and generating some phases. What is this? E raised to power j phi, correct. Okay, and phases and j phi into pi by 4. So the first value of this sequence, when you insert it, what will r of n be? E raised to power minus j3 pi by 4. Okay, so you are going to send that. Okay, correct. Okay, so if it is 1, you will send one sequence. If it is 0, you send another sequence. That's all. Fine. Okay, so and there are 30 such sequences are defined. So what are we saying? We are taking 1 bit, we are mapping it to one of these 30 sequences. Correct. Okay, right, and for a ACK, a particular base sequence R of n is sent. For NAC, base sequence is cyclically shifted by 6 and then used. Okay, so let's say if this is the sequence I am sending, okay, for the ACK. Okay, now what do I mean by sending this sequence? I will generate R of n according to this sequence. Okay, right, and then if it is NAC, what will user do? It will cyclically shift this sequence by 6 and then generate another R of n. Right, okay, so and cyclically shifted sequence is also a valid sequence, right. So what is happening here is you are basically, instead of 1 bit, you are sending, let's say, this 12 bit sequence. Okay, so what does it guarantee you? It is basically some kind of coding you are doing, right, and because of one bit you are sending some extra 11 bits. So that's the parity. Okay, right, and that's the best. People have realized that's the one of the best things you could do, because if you take, what kind of encoder will you design for 1 bit, right? Okay, and this is called code sequence design, and it's meant for sending these kind of small sequences. And at the receiver, what will it do? It will, if it has to find out whether it's an ACK or a NAC. Okay, what will it do? Okay, so that's what it is. So you take this UCI 1 bit or 1 bit UCI just for example. Okay, so your 12 length sequence is a complex sequence. Okay, you're not doing anything else after that. Okay, right? No QAM modulation, nothing, because this is like already a complex sequence, right? You substitute it over here, you are going to get a complex, it's like a phase, okay, right? So it's already some kind of, like, you can say it's a QAM modulation, because it's a complex number you are going to get and you are going to map it to PRB, right? Okay, and it is transmitted over the two-dimensional grid. I am not showing all that, okay, right? And that is also indicated using the DCI, by the way, correct, where this user is going to send its like PUCCH also, okay, that will also be indicated. Now, so it is received, it is demapped, and then what is this maximum likelihood detection? We learnt about it, right? One of these two sequences, okay, which one it is? So whatever, so you receive this, you basically calculate the distance, okay, and wherever, to whichever sequence it is closest to, okay, you declare that sequence as being transmitted, and you know that if it is an ACK, you transmit this, otherwise you will compare it with a cyclically shifted sequence. Only two possibilities for this case, okay, either this sequence or the cyclically shifted sequence. You will compare R of n, received R of n, with the transmit one of these sequences, and whichever gives you the least value, you will declare that whether that bit was transmitted, whether bit 0 was transmitted or bit 1 was transmitted. It's only minimum distance. Done, right? Okay. So you see that there is a separate transceiver chain defined for sending ACK or NACK, okay, because polar also requires certain number of minimum bits to work, okay, that's how it has been designed. Here it's only one bit, and this is a special transceiver chain for sending this kind of information. Fine, okay. So this is format 0, very simple, fine. So let's move on to format 2, okay. And if we understand format 2, then we'll basically understand a lot of things, and I'll not focus on other formats. There are other formats defined in the standard, but let's understand this, and then we'll move on, okay. I'm not going to cover any other formats. So what is, you look at the transceiver chain, okay. First, see, this is PUCCH transceiver chain. There are key difference between PUCCH and PDCCH transceiver chain. What is the first key difference? There is segmentation, which was not there in PDCCH transmission chain. There is no CRC scrambling is not there, right? Okay. You see this, then there is that interleaver which was there, it's not there, okay, correct? And the reasons are clear, okay. I'll again focus on that, but let's look at the complete chain, okay. So there is polar coding, there is sub-block interleaver, rate matching, there is something called channel interleaver, code block concatenation. So what I've shaded in blue are the new modules, other one are the old modules, okay, right? Scrambler is missing, and so modulation, okay, so QPSK, okay, and then demodulation, opposite of that, okay. Descrambler, concatenation, if you are concatenating blocks over here, you will basically segment these blocks, okay, so that you can work on different blocks, because what is happening here, you look at this, just to like, we'll jump the gun, this UCI can get segmented into maximum of 2 code blocks, okay, you see this, that's happening over here, okay. CRC, 2 code blocks, then polar coding for both of them, sub-block interleaving for both of them, rate matching for both of them, channel interleaver for both of them, and then code block concatenation, okay. Why? Because till from here to here, these modules work on 2 different code blocks. After that, as we have understood earlier also, that these 2 code blocks are concatenated and then scrambled and modulated, right? And reverse of that is happening at the receiver. So if it is concatenated, because the subsequent module, they work on code blocks, it has to be segmented, right? Okay. Then de-interleaver, rate recovery, reverse of that, okay. By this time we are comfortable with all this, okay. So first difference, PUCCH chain does not use CRC scrambling and CRC interleaving. Why? Because of the obvious reason that in downlink there is blind decoding, uplink there is no blind decoding, okay. Who is scheduling the data? Base station is scheduling the data, right? And who is the receiver in the uplink? Base station. Base station of course knows where all this information is coming, for which user it is meant, because it is only pre-decided, right? Okay, so if those aspects are not there, then you don't need scrambling and interleaving. That's how it is designed. Okay, see the difference. Okay. PUCCH chain uses UCI segmentation and also higher order modulation order. Okay, I'll talk about this higher order modulation. Okay, when does that happen? Okay. But Typically in the big, it is like QPSK when I am talking about format 2. It happens only in some special cases, we will discuss that. Okay. And this is, we looked at it in the beginning when we were talking about polar codes. Polar codes are used if the UCI length is between 12 and 1706. UCI, okay, I'm using, instead of DCI it becomes UCI now, uplink control information. So polar codes are used for this length, and for A less than 11 ad hoc codes are used. Okay. I just gave you an example, right? If it is format 0, that was an ad hoc code. Okay. Especially ad hoc means specially designed tailor-made code for this kind of information. Okay. Right? And then mother code length for the uplink is 1024. Okay. Right? And now maximum UCI length is 1706. Correct? What I am saying here is the maximum length you can send here is 1024. Okay, but the UCI information is more than that. Correct? Okay, so of course this UCI information needs to be segmented so that you can properly encode it. Because if 1024 is the maximum polar encoder can output, how will you take in 1706 and then encode it? Rate has to be always lesser than 1. Right? Input bits have to be lesser than the output bits. Okay? Maximum output bit can be 1024. And why it is so high in the uplink? That's what also, why this UCI length is so high, 1706. Okay? It is only like 140 bits in the downlink, and it's, look at this. This information is going up to 1706. Why? Because UE needs to transmit this something called channel quality information. Okay? Right? So we'll discuss that, what this channel quality information is, but typically MCS is also a part of that. Okay. Then we spoke about this MIMO, then there's something called precoder information which you need to send. I'm not talking about that because we have not spoken about MIMO. Okay. Right. So all that information UE needs to feed back, and that's why it is the length is high, high throughput. Okay, 1706 when compared with downlink. Okay. So UCI is segmented into 2 equal length polar code words. That's what I'm showing you here, and the reason for that, because when compared to DCI, UCI is basically can have a much higher payload. Okay. Now, so these were the like broad facts, okay, about the UCI. Okay, and then you have gotten the UCI. Okay, and then you want to like basically transmit it. Okay. Right, what is contained in UCI? We saw that MCS information, channel quality information. Okay, right. So once the UCI is basically decided, then it has to be segmented. Okay, depending on the particular length. Okay, so input to what we are discussing now is this segmentation block. Okay, I'm not going to focus on these blocks because they are all the same. Okay, right. So input to code block segmentation is A length UCI. Okay, this is how it is denoted, small a. Okay, I'm discussing how it is implemented in the standard. Okay, output will be how many? Either C is equal to 1 or C is equal to 2 segmented code blocks. Fine. Okay, and A can have any length. Okay, right. If you have to segment it into 2 code blocks, so it should be of even length. And what standard says is, if A is odd and C is equal to 2, okay, a single 0 valued padding bit is inserted at the beginning of the UCI. Okay, because you have to segment it, and you have to segment it into 2 equal length code words. So a 0 is inserted in the beginning, okay, of the UCI. Fine. Okay, that's what it is. So total number of PUCCH bits will be how many? If A is, let's say, odd number, okay, 21, we want to make it 22, right? So that's what it is. So you define A dash. Okay, if C is 2, let's say, okay, you want to segment it, then only you increase the length. That's what we are saying. Okay, so what are we saying? So A by C, let's say 21 by 2 becomes 10.5. C related becomes 11 into 2, it becomes 22 bits. So A dash is A plus 1. That's what it is saying. Okay, fine. And you have to basically, you are not always adding, it's not that A dash is always equal to A plus 1. That's why this fancy formula. Okay, it's not by default A dash is equal to A plus 1. So you should understand why we are doing this. Okay, if it's only odd, then and you have to odd and then it has to be divided into 2, then A dash becomes twice of A, or no, A plus 1, sorry. Okay, right? And what will the receiver do when it concatenates? Okay, right? So it will remove this code bit, it will remove this extra bit, that's all. Okay, right? So because that extra bit should not go from 5 to MAC. So what happens now? Okay, this is, I should have, each segmented code block has, this is not A dash, I thought I removed it, has how many bits? Each segmented code block has A dash is equal to, fine? Each segmented code block will have how many bits? A dash by C, right? Okay, so fine, and so the segmented code block is, it will be A dash by, each segmented code block has A dash is equal to A dash by C, and that next bullet is incorrect. Okay, so this is how it is. Okay, right? So each segmented code block has A dash by C bits. Okay, fine, right? Because that's what we have done. Okay, now let's not look at this. Okay, so this was the notation. Okay, now what are we saying here? Okay, so when will this UCI be segmented? I have not told you when will this be segmented. Okay, right? So, and basically this is the flag I segmentation is equal to 1. Okay, it will be set to 1. And when will this happen? Okay, if the UCI length is between 360 to 1706, okay, and the number of transmit bits which is allowed to transmit is greater than 1088. Don't get carried away by these numbers. Okay, they arrived after extensive simulations. Okay, so there is it gives the best performance. Okay. I don't have any more insights for this, for these numbers particularly. Okay, they are defined in the standard. And so what we are saying here is, okay, so the UCI gets segmented in 2 cases. Okay, what is this first case? This is the first case. Okay, what are we saying? If the UCI length is between this, fine, and this is the second condition, the number of transmit bit is greater than 1088. E is what? The number of bits you are allowed to transmit. Fine, okay. So if these 2 conditions are met, UCI will be segmented. Case condition number 1. Fine, okay. And second condition is if the UCI is between 1013 to 1706. This case is easier to understand. Right? Okay. Why? Because you see this, if A is close to 1024, you would like to segment it because maximum polar encoder length is 1024. Right? Okay. Here also, see this is, A is much lesser than 1024. Okay. Correct. One reason you can see here is that A is basically you want to segment it into two equal size code blocks. Okay. So if it is, let's say 1000, okay. So what will happen? Or let's say 1100, it again becomes close to 1024. So instead of taking 1000 and encoding it as 1024, you basically take it as divided into 2, 500, and then encode it as 1024. Okay, right? That's one reason. Okay. Now for these above 2 cases, it makes sense to segment when A is 1024. That's correct, because if A is, in both these cases, if A is greater than 1024, you would always like to segment it. You will have to segment it. Okay, because N max is 1024. Do we understand this? Okay. What am I saying here? In both these cases, if A is greater than 1024, you will have to segment it because N max is 1024. Okay. For first case, okay, when A is greater than 360 and much lesser than 1024, okay, and E is greater than 1088, that's the case we have in doubt, right? Because you see here, A is still less than 1024. Why are you again segmenting it? There is no need to segment it. Okay. What are we saying here? One could do polar encoding with 1024, right? And then repeat E minus n bits in the rate matcher. That could be done. Fine. Because what are we saying? Okay, you could basically, even if the length is like less than 1024, but E is greater than 1024, you can encode it with 1024 and repeat rest of the E minus n bits. Okay, because E is what? 1088, right? But segmenting it and performing polar coding without repeating gives lower PLER. And right, what are we saying here? Correct? If I, instead of repeating these E minus n bits, that is the first case, okay, which is not allowed in the standard. Okay, what are we doing? We are segmenting it and performing polar encoding. Okay, and so that you can basically, what will happen is you can repeat, you don't have to repeat the bits then. Okay, so that, and in that case it will give you a lower BLER. So these numbers, as I said, they are not magical, they are arrived after extensive simulations. So you don't have to get carried away by these numbers, but you have to understand a key idea what is happening here. Okay, right? So just to summarize, okay, that these are the two cases. Okay, and in this case, for the, it makes sense to segment when A is 1024, greater than 1024. In these two peculiar cases also, they are designed such that you get the best performance and the lowest BLER. So this is basically, this is how this segmentation module works. Okay, and now I'm going to tell you how it is defined in the standard. Okay, so let's look at this. Okay, so the input bit sequence code block segmentation is A0 to A minus 1. These are the number of bits which are going inside. Okay, right? If I segmentation is 1, so then the number of code blocks is 2. If I segment else, the number of code block is 1. What am I saying here? This decision has already been made, right? That whether the code block has to be segmented or not. Okay. So if, and this is, these are the reasons. Okay. This, if these conditions are met, basically, okay, these condition number 1, either condition number 1 or condition number 2, these conditions are met, one of this condition is met, then the segmentation will be enabled. Okay, right? And so let's say if the condition is met, then what is happening? Segmentation flag is 1, number of code block will be 2. Okay, right? Otherwise it will be 1. Now what happens here? What is this? A dash is equal to A by C into C. What is this? We just discussed that. When will this kick in? When C is equal to 2, right? And A is odd length. Right? I showed you this formula. This 0 gets appended in the beginning of the UCI, right? You remember this, okay? Fine, and let's read this. What is this? Okay, so if this condition is true, okay, let's say, so what is A dash will be equal to A plus 1, right? So where will this I run from? What is A dash? It is A plus 1. Both of them get cancelled, so I will be only 0, right? So A dash I will be, this first bit will be 0. Right? Okay, what are we doing? In the output, we are basically appending one extra 0 bit when this condition is true. Fine, okay. So you have to understand why this is happening, and that's what I told you. Okay. So this is basically appending that extra 0 bit in the beginning. Okay, right? And then what is this? You're just writing the sequence like that. Okay. What is this? A dash minus A to A dash minus 1. Where will this run from? 1 to A dash minus 1. Correct? What is A dash? Is A plus 1. A plus 1 minus A, you get 1. 2, what is that? A plus 1 minus 1. So it will run from 1 to A, that's all. So the length has been incremented, that's what we are saying. Okay, length, and how much is incremented? Is incremented by 1. Okay, and what is this? So you are taking the, it will be 1 and it will go to, this will be 0, it will go to first bit, first bit will go to the second position, that's how. Okay, so that's the change in index because you had to append this extra bit. Otherwise, you don't have to do that. This will not be applicable. Okay, so if this condition is not met, then basically input sequence is same as the output sequence. Okay, you can verify it yourself. That's what is happening. So what is this after that? So this part of the code is only for appending that extra bit, right? Okay. And this part of the standard, what is it telling you? Okay, so if basically C is 1 or 2, depending on that, you segment it. That's the segmentation. Simple. Okay, you take the block and segment into 2 blocks. That's what is happening. Okay, you set S is equal to 0. Okay, R is the code block index, which will run from 0 to C minus 1. Then K will run from A dash by C. A dash is the total length of the sequence now, correct? Okay, and the A dash is, so where will this index run from? this is the read index, okay. K will basically, so this will, K will run from 0 to A dash by C, okay, because you are dividing into two equal length, okay. And so what is happening here? You take the first 0th code block, K is the write index, okay. It will run from 0 to this one, okay. And what is this? S is the read index. Where is it running from? It starts from 0, gets incremented, go to the loop, okay. 1 goes to next index, S gets incremented, okay. So you keep doing this for the first code block. Then once K is over, your K is run from 0 to A dash by C minus 1, then you go out, increment R by 1, that is the second code block, do the same operation, right, okay. And then what happens after that? So we have segmented it. What is the next block? Next block is CRC. You will have to append a CRC. That is what it is saying over here, that the sequence, okay, right, this is Rth sequence, this is the length, is used to calculate the CRC parity bits. L parity bits are calculated according to some polynomial which is defined in this clause 5.1, the generated polynomial of length L, okay. So you append that CRC, correct. So for how many bits this is, where will this index run from? Because you have already exhausted from 0 to A dash by C minus 1. So this index will run from A dash by C to A dash by C plus L minus 1, that is all, okay. And what are you doing? You are basically calculating this parity and then appending it to the segmented code block, right, okay. So that is what is happening. So in this case what we have done here is, I have told you two key things, okay. One is that we have seen about two different formats, PUCCH format 0, other one is PUCCH format 2, okay. Format 0 is very simple, okay, it's designed for, it can have a maximum payload of 2 bits, okay. Here it is much more dynamic, okay. We came up with those numbers A, okay, right, and then based on that, based on the length of A, okay, we can basically either this code block this UCI has to be segmented or not, okay. And we came up with two conditions for which this UCI will be segmented, and those conditions are derived such that you get the maximum coding gain, okay, right. So and then the last two slides taught us how to basically segment this UCI, and if the UCI has odd length and it has to be divided into 2, one extra bit has to be appended to the beginning of UCI. That is the whole process which we have learned in this class, okay. We will continue discussing this PUCCH chain in the next class also. So thank you.